Alrighty, y'all. Today we're taking a look at the recitation for February 25th, right? And for this one, we're thinking more about forces, and this one we're getting into some friction stuff, right? It's going to be super duper fun, right? So, alright, we have two books sitting on a table. Each are 1 kilogram. We have some coefficients of static and kinetic friction, right? And we're exerting a sudden force on the bottom book, right? And again, we just intuitively, we know what's going to happen, right? Books are going to either accelerate together or the bottom book is going to get yanked out from under the top one, kind of like the magician pulling the tablecloth out from under all the dishes and stuff, right? So in case one, the type of friction that exists between the bottom book and the table, right? So if the bottom book is accelerating, right, on the table, so between the bottom book and the table, that's going to be kinetic friction, right? Because the book is moving relative to the table, right? And then between the two books, right, they're not moving relative to each other, they're moving together, right? So that's going to be static friction, right? And now in case two, right, between the bottom book and the table, again, the bottom book is moving relative to the table, so it's going to be kinetic again, right? And now between the two books, right, for this case, right, one's pulled out from beneath the other one and they accelerate at different rates, right? So this time they are accelerating relative to each other. So this one's also going to be kinetic friction, right? So now let's start thinking about some force diagrams, right? So I'm just going to draw a quick picture of my situation off to the side. Right, here's one book, and here's another. I'm saying A is on top and B is on the bottom. And here's our table. Ooh, that's a bad table. There we go. Wonderful, right? Here's our little picture, just to keep in mind which book is which, keep track. Right, so I'm going to draw a couple of force diagrams. Right, so the first thing, we're looking at the situation where the force is almost large enough to pull the bottom book out from underneath the top one. Right, so let's start thinking about book A, which is the one I said was on top. Here's our book A, right? The forces we have acting on it. We have gravity going down. Here's our FGA, right? And we have the normal force between book B. So this is going to be force of B on A, or force normal of B on A, right? And then also, right, we know it's accelerating this way. So the friction between the books has to be pushing it. I'm saying we're pulling them this way, right? So we're saying it's going to accelerate this way because that's what we said the top book accelerates with it. So we need some force there, and that's going to actually be our static friction of B on A, right? And now in book B, right? Here's our book B. We have gravity on B, and we also have, right, A pushing down on B, right, because we need an equal and opposite to this one over here. So this is going to be our F normal of A on B. Right, and then we have, right, some normal force from the table. I'm just going to call this regular Fn. And we know that since the book's sliding on the table, we said we have kinetic friction between the bottom book and the table. So we can put that one going against our direction of motion. That's our Fk on B, right? But also, we were talking about Newton's third law. I said I needed a force equal and opposite here because B is acting on A is acting on B. Same thing applies with this friction, right? So we're going to have force due to static friction of A on B, right? Same thing, our Newton's law, every action has the equal and opposite reaction, right? And we know that we want the book to be accelerating to the right, so that's going to be just our applied force, right? However hard we're pulling on the book, right? There's our applied force, right? So, right, the reason that our static friction's pulling us forward in this case, right? If book A wants to stay where it is, but book B is pulling it along, right? Book B, really, A wants to move this way relative to B, but B has to pull it along with it because that's where we said our direction's going. That's why our static friction is acting like this. And also it just has to do with, we know we're trying to accelerate to the right, right? We said, right before it's large enough to pull the bottom book out from under the top one, we're saying they're accelerating together at the same rate, right? So we know that sum of our forces has to be to the right for both of our books. I'm just gonna move that up a little. Now we calculate how much force is required to do this, right? So let's start doing our Newton's laws, Newton's second law, right? Our sum of our forces. So I'm going to start with A, right? So sum of our forces in Y on A, I'm going to say AY actually. Sum of our forces on A in the Y direction is, right, we have our normal force acting positive. I'm going to say this is positive and this is positive, right? Set my constant axes. And we have our Fn BA plus our negative MGA, or MAG, negative MAG. Does it say they're both the same mass? Oh yeah, they're both the same mass. So we don't have to specify which mass is A and which one's B, but I'm going to do it just for the sake of keeping track of things, right? So that's going to be our mass times our acceleration in the Y direction. And that's A, right? Now our sum of all forces on A in the X direction, right? That's just that one right there, right? So our Fs BA, that's acting in the positive direction, so it's fine, and that's MAAX. Okay, now let's look at B, right? So our sum of our forces on B in the Y direction is, right, we have our normal force from the table acting up, and then we have our gravity, it's going to be in the negative direction, MBG, and our normal force from AB, normal A on B, right? And that equals our MB is our acceleration in the Y direction, right? Now we do our, ooh, that is quite the sigma. Some of our forces on B in the X direction, right? This time in our positive, we just have our applied force, so I'm just gonna call that FA. Remember, we're asking how much force is required to do this. This is what we're going to be solving for, right? And now we also, acting in our negative direction, we have our force due to kinetic friction, right? And our static friction from the book, the other book, Fs A on B, right? That's our MBAX, right? So now let's start thinking about what we do and don't know about these forces, right? So we can say our acceleration in the Y direction, right? Our books aren't flying up into the air, right? So all of our AYs just going to go to 0, right? Wonderful. And I marked our AX and our AX as the same, right? Because we're saying that they're accelerating together at the same rate, right? So we can keep those as the same variable, right? And what else do we know, right? We're saying a situation where the force is almost large enough to pull the bottom book out from underneath the top one. What that tells us is that our static friction, right, is at a maximum, right? Because our coefficient of static friction, right, up here, that gives us a maximum value for when the static friction is at a maximum, because before it gets to the maximum, it's just going to be enough to stop the thing from moving, right? So right now, since we're saying it's the maximum amount of force, and the force is almost large enough to pull the bottom book out, that we can say, right, our force from static friction, BA, is going to be our coefficient of static friction times our FNBA, right? We can say this because we want our static friction at a maximum because our force is almost large enough to do this. This is like our threshold, right? So now let's start doing some math. And we can say the same thing over here about our static friction on this side, right? Over here, right? I'll plug that in a little bit, right? So let's start solving some equations, right? So I look over here. I have our FNBA minus MAG is 0. Right, so if I solve for FNBA equals our MG, right? Now I can take this, plug it in down here, right, to solve for our everything down here, right? So if I plug this in for here and this in for here, it's going to give us that our mu s mg equals ma. I'm just going to leave it as a, right? Because we know we're not accelerating the y direction, we're just accelerating the x, just making it easier on myself. Wonderful, right? So now flip on over to these equations, right? We can do something similar, right? Because we know some of these values now, we can start plugging in. Right? So our Fn minus mg plus our negative, it's going to be minus actually, but right, our NAB over here, we got already because BA and NB, they're just opposite directions, and we've accounted for that opposite direction by subtracting it. So that's just going to be another mg, right? Again, because the masses are equal. So right, are in the y direction, it's 0, right? So now we can say, I have to move the equation a little further out of the way, but, right, our normal force between our book B and the table, that's going to give us 2 mg. Wonderful, right? So now we have some more information we can plug in down here. Remember, this is what we're solving for, right? And we're trying to get information about the rest of these unknowns, right? So our FKB, right, that's just going to be, right, our FK is our mu k Fn, right? So we have our Fn now. You can plug in with our mu k over here. And our FSAB, right, that was the opposite of SBA, right? So we can plug this in, or really down here, plug all this in over for here. All right, so let's start plugging all this in. Right, we have our FA plus our minus, and we said this was our mu k times 2mg. And then that's minus our maximum static friction over here, which was our mu s mg. And that equals our ma. Cool. So, right, in this equation, we know g, we know all of our masses, and we know our mu k's and our mu s's, but we don't yet know this acceleration. But we have our acceleration in terms of things that we do know. Right, so I'm going to divide both sides by m and get that a equals our mu s g. Right, and now I can take this, plug it in on over here. Right, so we're going to get fa minus, I'm just going to flip this around a little, so 2 mu k mg minus mu s mg equals m times mu sg. There you go. Right? So now we know everything in this equation except what we're solving for. One equation, one unknown. Wonderful work. We can solve this now, right? How much force required? That's our, whatever our applied force is. So let's start plugging in some numbers, right? So, right, I'm going to solve this real quick for FA as well. So we get FA is going to equal m mu s g plus 2 mu k mg plus mu s mg. Cool. So, all right, Fa, our mass is 1. All right, and our mu s, you can come back up here, coefficient of static friction, 0.4, right? 0.4 times 9.81, right? Plus 2, our mu k was 0.2, right? Right? Not plus yet. That's our mu k. Now we have our m and our g again, right? Now plus our mu s once more, 0.4 times our m times our g. Now, multiplying all of this out, I don't really want to do. So, I'll leave that up to y'all if you want to just punch this into a calculator and get an actual value for your Fa. All right, that's just how we go about solving it. All right, so now let's move on to our next problem. We got some cats, Fifi and Tally, I don't know. I'm gonna say, pick one. We're going with Tolly today. Tolly. It's a tall cat, right? We have the coefficients of friction, right? And we have their masses, and we have, right, our changing angle theta between our table and the horizontal, right? So 2 things about friction that we're going to remember. 2 things already sliding past each other. Force of kinetic friction is equal to our mu kFn, right? And our directions opposing the motion. That's the thing we were talking about before, right? We can just say our Fk is uk, right? But if it's not sliding, the force of static friction is however big it needs to be to stop them from sliding, right? And the maximum is with our coefficient of static friction. So now let's draw a cartoon of this problem, right? And we're choosing our coordinate system, right? So we have our table. I'm just going to draw it at an already angled theta. That is not horizontal. All right, here's whatever theta is, right? And here's our cat. And a little tail. There we go. There's our cat. And I'm going to say that my axes are tilted, right? Because we said that's our easiest way to do some of these tilted problems. So I'm going to line them with perpendicular and parallel to the table. And right, our theta is increasing, so the table is going to be tipping up like that. Okay? Saying up is positive and right is positive for this. So here's our cartoon and coordinate system. Right? Again, this tilting the axes makes life easier in the long run. Right? So now we draw a force diagram. Right? Force diagram for both of the cats is going to look the same. Right? So I'm just going to draw one and we'll apply it to both. So we have, right, force diagram, right? Right here, here's our cat. We have gravity going straight down. And we have, if our table's like this, we have our normal force there. And we also have some kind of friction, right? I'm going to just call this FF right now, right? Because that's just going to be our friction, right? No matter what it is, it's going to be parallel to the table and acting up the table, right? If it's kinetic, it's going to be because we're already sliding down this way and we're being pulled back. But if it's static, this is what's going to be stopping us from sliding, right? So now let's real quick break these into some trig components, right? Because these are not currently aligned with how we set up our axes, or at the very least, G isn't aligned with how we set up our axes because we have these two that are already parallel and perpendicular to our table, right? So I'm going to break FG, right? So we'll have this here. I'm going to break it into this way and this way components. There's our right angle. Right, and here's our theta. Right, so if this is our FG, here's our FX, and here's our FY. Right, so right, our FGX is going to be FG sine theta, and our FGY is going to be FG cosine theta, but negative, right? Because I said up was positive, so that's going to be negative there, right? And now I'm just going to redraw this force diagram with our components to make it easier to visualize later, right? So here's, if I draw the table here, right? And we have our normal force and our friction force and our gravity in the x and our gravity in the y. So this is FGX, FGY, Fn, and whatever kind of friction we have. Right? Oh, well, I kind of skipped the next step, or I didn't skip it, but I jumped ahead a little bit, breaking our force due to gravity into our components. Right? We drew our right triangle, and the weight has to be the hypotenuse. Remember, we were talking about that. Whatever we're breaking into components has to be the hypotenuse of our triangle. Right? And the legs are going to align with the coordinate system. Right? So, well, it does say do it on the diagram above, but we already did this. So now we're going to do Newton's second law. Right? So some of our forces in our x direction, right? We have our gravity acting positive in our positive x direction, and friction acting negative. So it's going to be, all right, FGX, which we said was our FG sine theta, mg sine theta, with our negative force from whatever kind of friction we have. Right? And that's going to equal our MAX. Now we have some of our forces in the y direction. Right? And acting in the y, we have a positive normal force and a negative FGY. Right? So Fn with our negative mg cos theta. It's going to be our MAY. Right? There, we have our Newton's second laws. And we know our masses. Those were given up in the problem. We don't know our friction just yet. We don't know our thetas just yet. So we have a lot of things to be figuring out, right? Right before the cat slides off the table, what's true about the frictional force, right? Right now I've just been labeling it as general friction, right? But before it starts sliding, right before our cat starts sliding, right? It hasn't started moving yet. So first of all, we know before it begins to slide, it's going to be static friction, right? Because it hasn't started moving, we're at static friction, right? But if it's right before this cat begins to slide, that means our static friction has to be at a maximum, which means we can say that our force from friction, as I've been writing it, is actually our force from static friction, which is going to equal our mu s Fn, right? When it's at this maximum, we can use the mu s and we use our normal force, right? So now we have more things that we know. We can solve for our theta, right? Because that's what we're looking for. Find the angle at which the cat begins to slide, right? So let's look at, right? We're looking for each cat. So I'm going to start with, I'm going to pull my equations down first, right? So you have this. Get rid of those. And over here we'll do Fifi and Tolly. Right? So if we're plugging in things that we know, right, this one is going to be mg sine theta minus, we said it was mu s Fn equals that says max. And since it's right before it starts sliding, we don't want the cat to be accelerating just yet. So we're setting that equal to 0. Wonderful. Okay. And now we're going to do over here. Right? Same thing. We don't want our cat to be sliding just yet. So Fn minus our mg cos theta, that's just going to equal 0 as well. We don't want our cat to be sliding yet, so that's why this is 0. But this one is because we don't want our cat's not jumping up off of the table. It's just sliding down parallel. It's not moving perpendicular to the table. So I'm going to solve this for Fn. Right? Fn is our mg cos theta. Right? And I can plug this in up here for our Fn. We get that. And if I just bump this to the other side, I'm going to say our mg sine theta equals our mu s mg cos theta. Right? And now in order to solve for theta, we have to kind of combine our different trig functions, right? So I'm going to divide both sides by m and divide both sides by g, right? I'm going to get sine theta equals mu s cosine theta, right? So now if I divide both sides by cos theta, sine theta over cos theta equals our mu s. Sine over cosine is just going to be tan theta is our mu s, right? Which means theta is going to equal our tan inverse of mu s, right? That's going to be true for both of our cats, right? Because I didn't plug in any numbers just yet. All we know is that we don't want the cat accelerating yet in the y. We know it's at a max static friction, and it's not jumping up off the table. I've not plugged in any numbers, so we could just apply this equation to both of our cats, right? So for Fifi, our coefficient of static friction, if you go back up, Fifi is 0.5. Right, so we're going to do theta is the tan inverse of 0.5. Right, and that means our theta is going to be approximately 26.5650518 degrees, cutting for sig figs 26.6 degrees. There we go. That's our angle that Fifi starts to slide at. Now let's take a look at tally, right? Our coefficient of static friction for tally is 0.4. So we're going to be doing the tan inverse of 0.4, right? Which means that our theta is going to be approximately 21.801404949 degrees. Cutting for sig figs again, theta is 21.8 degrees, right? There. Which makes sense, right? If our coefficient of friction, of static friction, is lower for Tally, meaning she slips easier than Fifi does, right? She's gonna slide at a lower angle than Fifi is. Fifi's gonna hang on just a little bit longer than Tally. So those answers make sense, right? Now, right after Fifi begins to slide, what is the acceleration, right? So now, before we said we don't want to slide in our x direction just yet, right? But now we do want an acceleration in the x direction so we can solve for it, right? So I'm going to pull this equation, right? And I'm going to borrow this equation as well, right? Oh no, I lost part of it. Missed part of the f. Right? Now we rethink about what's going on, right? Because before we said this was right before the cat begins to slide, so we set this up, right? But now we're sliding. We're already moving. So, right, our friction now, since we've already begun to slide, it's going to be kinetic, right? So that's going to be our Fk, right? And we know that our Fk is our mu k Fn, right? So now we start plugging in things that we need to solve, right? So down here, we still want our A acceleration to be 0, right? Because we're still not jumping up off the table, but cosine theta equals 0. But now our x direction, right? This is the acceleration that we're solving for, right? acceleration sliding down the table. Right, so if I plug in, I have my mg sine theta here, and I plug in what we said, our friction, our mu k Fn. That's going to be max. Right? So now I'm going to solve for Fn down here and plug in to my equation up here. So you got Fn equals mg cos theta. Right? That's going to go up in here, the mg sine theta minus mu k, and then we said that Fn was mg cos theta, mg cos theta equals max. Right? So there's the equation that we end up with. Right? So then we're solving for our acceleration. But we said right after the cats begin to slide, right? Which means our theta is going to be our theta when they start sliding. Right? So we know that this is the instant that they start sliding. So we can use that as our theta down here, because this is right after that, like the instant after. So, right, here's our equation. Plugging in our various thetas and things, let's look at phi, and let's solve for that acceleration. I don't know why I said it like that, but, right. Again, I'm going to be able to just divide through by our mass of the cat. So it doesn't matter what the cat weighs, doesn't matter the mass of the cat, all that matters is our coefficients of friction and all that jazz in our thetas, right? So our mu k for phi, 0.4. Right, so I'm going to start plugging in these numbers. So we're going to say g sine of, you said it was 26.6? Yep. G sine 26.6. I'm going to write G is our 9.81 as well, right? Minus, we said mu k was 0.4, right, times G times our cosine of 26.6 again, right? And that's going to equal our acceleration. So for phi, we get our acceleration right after she starts sliding is going to be about 0.86669999481 meters per second squared. All right, and then cut for sig figs, 0.867 meters per second squared. There we go. There's our acceleration for phi. Cool. Now let's do the same thing for Tolly. Right? Tolly, I'm stealing the same equation, right? When we cancel out mass, we're just plugging into it again. Tolly has a coefficient of kinetic friction of 0.3. Right? So we're going to say, right, it's our 9.81, it's our G, times our sine of, was it 21.8? I don't know why I put parentheses around that, it's fine. Minus our mu k, which we said was 0.3, times our 9.81. Oop, I'm running out of space. Drag this down here real quick. 21 times our cosine of 21.8, right, and that's going to give us our acceleration. Right, so that's going to work out to be about 0.91083563338 meters per second squared. Right, and rounded for sig figs, 0.911 meters per second squared. Right, there's our acceleration for Tolly, which again, right, it makes sense that Tolly's going a little faster because she has a lower coefficient of kinetic friction. Right? She's more inclined towards slipping than phi is, so she's going to be going a little accelerating slower. Right? So now we look at friction force versus our tilt angle. Right? So this is what we're calling our theta. I'm just going to switch to red so it stands out on the graph, but this is our theta. All right, and this is our whatever we were saying our FF is. Force of friction. Okay. So, as we go. All right, here's when we have a 0 tilt angle, so this is where we're starting from. It's when our table is fully horizontal, right? And right here is our maximum force of friction, right? We know that our mu s is always going to be greater than our mu k. What that tells us, right, is that at this theta here, right, our mu, whatever it is, right, because our mu is in our static friction zone is just whatever it needs to be, but this, at this point, it's going to be our mu s, our maximum static friction coefficient, right, because that's going to give us our maximum friction force, right? So as we're going up here, if this is our maximum static friction, that means before here, this is when we have our static friction, right? And our mu the entire time is going to be increasing, right? Because our mu increasing, right, as we go, we have to, like, our friction force is going to be, it's going to need to be greater as we need to go more. I'm not explaining that well. Our mu changes based off of how much friction force we need to not move, right? So our mu increases as we need more friction in order to not move. So this entire time we're in static friction, our mu is going to increase so that we don't accelerate, which means also down here, right? Since everything's just equal to 0, right? Our mu here equals 0, right? Right? That means that if right after we get to our maximum static friction, right, this zone right here where it drops, it's going to be our start of our motion, right? This is where we start moving, right? Because once we get over that initial hump of static friction, kinetic friction, our coefficient of kinetic friction is going to be a lot lower, right? So this is where, for the rest of it, our mu equals our mu k, right? And our mu k isn't going to be changing, right? Because our static friction is whatever we need it to be, but mu k doesn't change, right? Right? Equals constant, right? So mu equals mu k, that's this entire zone over here, right? That's the whole, I don't know why that looked so gross. That's the whole rest of our what's going on, which means that over here we're in kinetic friction. All right, well, if our mu isn't changing, then why is our friction force still decreasing, right? Because over here we said we were increasing our friction force because our mu was increasing, right? But we're still changing our tilt angle. And our kinetic friction, remember, like, our friction force doesn't just depend on our mu, it also depends on our normal force, right? So over here, like, our normal force is decreasing, right, as we go, because we were saying that our normal force, right, if we're not accelerating in our y direction, our normal force is our component of gravity. That changes with theta, right? So it's decreasing, but our mu is increasing more than our normal force is decreasing, so we get this slope. But right now, our mu is constant. So now all we're seeing is that decrease in our normal force, right? Because as our theta is going to keep increasing, this cosine is going to decrease, right? So as we go, that's going to give us our decrease in our normal force, which gives us our decrease in our friction, right? And those are our, right, that's our things to look at, right? That's just a big thing to mark, right? The entire time, our Fn is going to be decreasing, right? That's going to be happening the whole time, right? Starting at the beginning, that's going to be happening. But, right, our mu s changing accounts for that here, but, right, since it's constant over here, it's not going to account for that anymore, right? Because our Fn is our mg cos theta. Right. All right. Well, I hope you found this video at least a little bit helpful. Let me know if you have any more questions about this or any other problem that you want me to try to explain, and I'll do my best to try to explain it because I guess Sydney explains stuff.